So it has an analytical solution to it, and it's a bit messy. So let me just follow it. Okay. Some of you might have learnt about this in your bachelor's final. So as many infinite terms you can take. So indeed, it is like a very complicated equation, but our aim is not that. Our aim is something else. Writing it so that we can actually compare our numerical method solution with analytical. I think some of you might have seen this kind of equation, the heat equation, if they have solved in their bachelor's PDE. Variable separable method you have learned. So you can solve this by the variable separable method. Okay. And you theta kind of. So I won't urge you to look into the proof. I won't. Okay. Because the course is not designed for that. The course is only for the how to solve this equation using numerical methods. So we maybe like three schemes. One is explicit scheme. So this method can be solved using the explicit scheme. All right. One time step depends on the state at n step, right? Then the implicit scheme. Solving n plus 1, you will need the points of n plus 1, right? So that's like implicit. Then implicit and implicit scheme. Generate another method, and it is even more nicer or more efficient. Okay, so that's known as crank Nicolson. So, to be honest, you can develop many methods, huge number of methods via this procedure, like a combination of explicit and implicit. Can you imagine why? Taking some part, some X part of explicit and some Y part of implicit to make, right? And X plus Y will be 1, right? So the coefficients, okay, like 100% coefficient. So it can be 0.1, 0.3, 0.7, 0.5, 0.5, 0.51, 0.49 expected through this scheme. So, but they found that if you take 50% of this and 50% of that, it is an efficient scheme. They have done a lot of calculation, which we will do just for one, then we will not do for the rest too. Okay. So I will need your patience for the next 30 minutes. Okay. Like here also you will discretize your domain. Your domain here. Again, I will write the equations. Dou t by dou t equals to alpha, dou t2 by dou x2, right? What's the first step you should do? Apply finite difference. Apply finite difference to each of the partial derivatives. Finite difference formula for this. You know the formula for the second order partial derivative. What should I write for this? Imagine the grid now. The grid should be in your mind. Yes. By the step size. step size delta t. Why? Because it respect to dot t equals to alpha times. Can you tell the second order partial derivative for the finite difference? Should always visualize see, you don't have to remember the formulas. It's just the way of mnemonics. But through mnemonics, while seeing this problem, the grid should be in your mind. What I should do? Take the point on the left. If I am I, what is my left point? I minus 1. Yes. Then you know there is a 2 times of I plus my right. What is my right? Ti plus 1. Divided by, there should be delta x, dou x. So it will be the delta x term. So one more thing I am missing here. Here I have written n plus 1 and n, but here I have not. Guys, your method will be more explicit. Okay. So explicit scheme will be if your method is explicit scheme. Explicit scheme, it will be alpha. All will be depending on the nth step. Yes. With this, yeah. But also I'm missing something else also. Anything else I'm missing? This, so always there will be error. Always there will be error. We usually neglect it unless we do some analytical calculation, but always there is an error. Since we are using this finite difference schemes, so order. Okay. These errors are looking like this, but it's not mandatory for you because you are doing more of like numerical stuff. So it's not mandatory for you to actually go deep into this, but to know that it exists. Okay. Can you simplify for Ti n plus 1 from this equation? What is Ti n plus 1 looks? Can we see? This guy here, right? That you can keep on the left and take everything on the right. So can you tell me what it looks like? So check with me. N plus 1 will depend on Tin because this guy is there. Plus something else. What is that? This chunk. Agree? So this is your solve the heat equation. So therefore, I suggest you that the finite difference schemes are very powerful. See, I just used the finite difference scheme and I just, within 2, 3 lines, I just developed a numerical scheme, which you can enter now in your code and actually generate a color coded plot, how heat is diffusing. So therefore, you can see the link, how they're linking from like math and then to coding. Yeah. So, yes. One more thing I want you to visualize is yeah, I will show you the grid, how it looks like. So better appreciate this method. Let me draw the grid first. Right. So let me denote the point by red, which I'm trying to find. So this is the I'm trying to find here. All right. Some more notations. So x is here, and this is your time. And this is your time. How each heat, like the temperature, is varying with respect to time in each of these columns above it will go. Okay. And this guy, since this is x, this will be your I minus 1. This will be your I. This will be your I plus 1. Ti n plus 1. See, this is your nth step. This is your n plus 1 step. Yeah. Yes. So Ti n plus 1 is depending on Ti n. Yes. Then Ti n, Ti plus 1 n. Point. We need help from these 3 points. Yes. So this is the graphic visualization of this formula. Okay. Yes. So a very interesting thing of this formula is when you simulate this in your program, like if you take some problem is given to you, if you take delta x, say 0.2, okay, solve the system, it is running very nicely. Believe me, it will run very nicely. You get very nice solutions, lot of graphical. A very interesting that decreasing, this is a very big step size. I should decrease the step size so that my solution is even more accurate. Okay, that's what we have seen since our last semester. Yes. So what? Then you run your code. Then okay. So suddenly you will see that like spurious oscillations are coming, and that your code is not running fine. Okay. So solution converges. Okay. But here you will check that your solution is diverging. Then that if we decrease the step size, we will get some accurate result. But why it happened? So this is the motivation of showing that this method is conditionally stable. Okay, we'll see that this method is only stable if something happens. If some condition there which happens. And if you take 0.01, that condition is violated. Hence, your solution is not converged. For this method, it doesn't mean that you should stop choosing less. Yes. So this um, was found by Nicolson in 1906 around. Okay. So this phenomenon, like this bizarre phenomenon, was found by Nicolson, and hence he came up with a new method, Crank-Nicolson. Of size to a large extent diverging solutions. Was by Nicolson. So another analytical result which I want to tell, but again, it's not numerical, but I want you to know. So which is known as like a theorem, Lax equivalence theorem. You don't need to know, but understand. So everywhere you will be learning about these three things: convergence, so consistency, and stability. Okay. So we sometimes use these terms quite interchangeably. Okay, so we'll actually see what each of them means. So in a numerical method, you should actually know these three: convergence, consistency, stability. What is convergence? If your numerical method, in your numerical method, the numerical solution is converging to the analytical solution, then we say that yes, your numerical method is converging as your step sizes like delta x for PD are going towards 0. So considering a huge mesh grid, in that case, it is likely that your numerical method should converge to the analytical. Yes, more accurate. And if it is the case, you can say that it's converging. Okay. Consistency. So I think you have learned a lot about these errors in your previous semester. So few round of error, truncation error. Yes. So if your truncation error is going towards 0, then your method, numerical method scheme is consistent. Yes. One might imply the other, but A to B, but not B to A. The situation is like that. Okay. So yes. So stability, can anyone say? So stability means if in your numerical scheme, random errors, if your numerical scheme doesn't allow random errors to grow in time as time progresses, then your numerical method scheme is said to be stable. So it doesn't allow random errors to grow. Yes, then your method is said to be a stable one. Now, looking at this definition, the explicit scheme is stable. Based on the definition of stability, can we say that the explicit scheme is stable? That's the question. What do you think? Not right? Because I told you that if you took delta x to be 0.2, your method is converging. But when you took delta x to be 0.01, your method started diverging. It's stable. Okay. Sometimes it is stable, sometimes it isn't. Therefore, we have to find a scheme when it is stable. Yes. You can understand the link now, how it is linking. Any issues, any queries? If you want me to explain one more time. I defined all these three quantities is because it is known as someone might have heard X equivalence theorem. Again, you don't have to. It's not mandatory for your knowledge. For a linear PD, your PD must be linear. For a linear PD, and it's an initial value problem. Finite difference scheme which you are adopting to the PD equations, okay, is convergent. Okay, the finite FDM I'm writing, the FDM means finite difference method is convergent. and only if and only if consistent and stable. Yes. So you can see now. So all the three terms are being used in this theorem. Convergent is used, consistent is used, stability is used. So your finite difference method you are employing, then the method is convergent if and only if consistent and stable. All right. Now you know that when a numerical method scheme is convergent. Okay. So there is a proof for this. We are not going for the proof. That's not the aim here. All right. So till now, any issues? When we saw that the explicit scheme, which we just saw here, we saw that reduction of step size, delta x, reduction of step size, random errors to grow, right? Which I showed to you just now. Okay, delta x equal to 0.2 and delta x equal to 0.01. Now we take this is the only proof we will do in the class. The other two proof for other. Okay. Right. So let's shall we move? Yeah. So so we are now doing the most important one, and I think you can appreciate it better. So we are doing the stability of explicit scheme here. Also coming under two different names in different books. One is known as the von Neumann stability analysis, or it is also known as Fourier stability analysis. Let's see why the word Fourier is used. We are not going to use any Fourier theory here, but the most of will be used for one or two lines. Okay. All right. So what was our method? Let's rethink our method. What equation? Ut say ut equals to alpha uxx. What I have changed the notation here. Alpha dou to u by dou x2. Same equation, right? So we have this equation. And using that explicit method, can you say what is the equation you got? U like ui n plus 1 plus r times ui minus 1n minus 2 ui n plus ui plus 1n, right? Where r is a new quantity for you. It is alpha delta t by delta x square. This is a very nice quantity, and your condition of stability will exactly depend on this quantity r. You will see. Therefore, we have kept it in a very nice box like r variable. Okay. Now there are two questions. We have to find the error for this method. Okay, for that, you see how the proof goes. Okay. Your method is done by 100% accurate. 100% accurate. There is no chance of error. Right? So, like an infinite precision machine. You beyond that you can't go, right? But assume that you have infinite and you get a solution. Okay, that is some solution, and you are running the same finite precision machine. Okay, and when you take the difference between the two, then you can see the error. Yes, it's the basic idea, right? So that's how we can like take the error out of this method. That's the basic idea which will be going on for next 15 minutes or next 10 minutes. All right. So assume that you have a solution D. If we have like a solution D, okay, solution D, and this is suppose the infinite precision. Yes. And then we have another solution, say solution N, infinite precision machine. Okay. All right. Now your solution is, that means it will follow this formula, right? It will follow the finite difference formula, right? So that means since it's a solution, I can write din plus 1 equals to di plus r times di minus 7. Now, since n is also a solution, we will have a similar sort of. That means we'll also have this. Now, can anyone suggest what we shall do? So, what I talked with you verbally just 5 minutes before, I am doing that now. I took an infinite precision machine. I took a finite precision machine. I found the solution from both of them. Take the difference. Take the difference. Because we believe that infinite precision would give us correct. Finite precision will give us some erroneous result. So if we take the difference, then we will get like the error term. All right. Yes. So we'll take the difference. The difference we will take like maybe n minus d. Say a new error is denoted by epsilon and it is n minus d. All right. The difference between n. Can you tell how it looks if I take the difference between of this and this quantities? N plus 1 equals to epsilon I n plus the r will be the same. Right. Now how we can keep track of and the error, growth of error. The, that we have to keep track. So therefore, motivated, we will define another quantity known as the growth amplification factor. Okay. So it is denoted by G. So G will be epsilon I n plus 1 divided by epsilon I at nth. Makes sense. If your error is growing with time, then mod G will be greater than 1. Can you see why? If your error is growing with time, epsilon I n plus 1 will be greater than epsilon I n. Error is decreasing over time, then G will be less than 1. We need G less than. See, everything is following based on intuition. Nothing new we are doing. Any issues? So can you find the expression for this as a as your right hand quantity and you're dividing by epsilon I n? Can you tell me what this quantity will look like? Yes. So enough time. Anyone got the expression? Should write. You should not always wait for the black pen to write. It will be like this expression. I have it here, so I will write directly. Uh, epsilon in. So this quantity is getting cancelled and we are getting left with -2 plus epsilon I plus 1n divided by epsilon in. Are you getting this quantity? Now for this scheme to be stable, see, G can be positive or negative also. So for this scheme, for the scheme to be stable, value of G, and it should be less than equal to 1. All right. Either the error should be constant or less than that, or should decrease, but should not increase. That's the idea of the stability. This part of the lecture, I want you to write a bit, because if I go to the next, right? So now what I will do is, what I should do next. Observe whatever I am doing. Okay. See, this is the equation. Compare both of them. Instead of u, just use the epsilon, isn't it? So that means epsilon is behaving like a solution of the PD. So that fact we are going to use. The solution of the PD. So that intuition, that logic we are going to use. And heat equation, this is one thing which you don't know, many of you don't know. That initially I showed you an analytical solution comprising an infinite series of signs. Yes. And I told you that you can use it like the variable separable. By variable separable, I meant that if your solution is ut comma x times like some u1t times some u1x, that is sorry, u2x. All right. So that is like a variable separable method. Okay. So that means you have a completely separate term for the t and a complete separate term for the x. Error which is varying with time, epsilon t comma x, can be written as, so similarly, epsilon t comma x will be like epsilon 1 t times epsilon 2 x. Fine with that? So this is the only part throughout the course where you need to make patience. Okay, because we are showing a bit of mathematical stuff. Try to be patient. Okay. Got this. What should we do? We can take the partial derivative with respect to x, right? Okay. So what is epsilon t? Epsilon t, that is dou e by dou t, dou epsilon by dou t. What it will look like? Check. It will be epsilon 1 prime. That is, I'm using prime because it is only one variable. The partial derivative dou epsilon 1 by dou t is the same as d epsilon 1 by dt, because epsilon 1 is only a function of time. Okay. So I have written epsilon 1 prime times epsilon 2. It will not get differentiated. be epsilon xx, epsilon 1 t times epsilon 2 double prime x. All right. Till now it is okay. Any issues? What shall we do next? Can you suggest? So here there will be a bit of into play, but let's not go. I just want to write the solution here. Okay. All this only to get to a condition. Okay. Now you might be thinking why we need to do so much of things, but only to get that condition we have to do so much of things. What I can suggest to you is you can check that you will see negative of a squared quantity is negative, right? So you can do some calculation, what I meant to say. Okay, I will not do it. So constant at a negative quantity, negative, this is negative. Okay. All right. So again from this, right, that epsilon 1 will look like some a like minus lambda square t. Why this is the case? Because epsilon 1 is only a function of time. Similarly, you can write epsilon 2 function of x as like, yeah, some complex stuff. Quantity. I am not using because I we are using for indexing. So therefore, I have used j here for denoting the complex number iota. So I want to show that this is indeed the case, like the solution for that. You can indeed solve. Why we can actually solve this? Because of this variable separate. Else it is not possible. Okay. So yes. So this is just one of the errors. There can be a lot of error also. So therefore you can take a summation of them. That is like the modes and all, Fourier modes and everything. So that's why the name comes here, Fourier. All right. We are not going too deep again into that. So since you now error term explicitly, now he was depending on these quantities here. Quantity. Yes, that's what is our goal. So yeah. So again, going into detail, but I'm showing you that now know the error terms. Hence, you can substitute and compute the G expression. That is the sole motive. Okay. Check that you will get the very nice form. Okay. And here I want you guys to plot this function. A lot. Does it give you hope to simplify more? Any ideas? What you can write again? Sine square you can write. Class 12th. Sine square beta by 2. Or versus beta for values of R. Can you plot G versus beta for different values of R? Or shall I give you this an assignment? Shall I give you this as an assignment, or shall I show you a quick way to do? You can always do in Python. Okay. All right. So here we have taken the quantity and we are trying to see the behavior with respect to different values of R. All right. Here here is the quantity for you. R is like, change it to R. That doesn't matter. So I think we have a problem. Like R is predefined here. Right. So here, as you can see, like for selected values of R only, our solution is lying within the strip where mod G is less than equal. If I vary the value of R, it is coming outside of the strip. That means your error will grow. Mod G will be greater than 1. That means your error will grow. Some are not even lying on the strip. So just as this, yeah, there is a tiny interval where only your method is stable. All right. So that was that. This is your just a graphical interpretation. So now we'll move to the analytical. Okay. So now we did a plot for different values of R, right? I encourage you to do that in Python. What we saw as a movie, I encourage you to do that in Python. Since we got this idea, cannot take delta x too small, delta t too small. There is a range you can take, and it should satisfy this quantity. Right? Yes, delta t cannot always be small, delta x cannot always be small. That's the main motivation to do all this math, right? So therefore, since there is a condition, this is known as conditionally stable. So explicit method is conditionally stable. All right, learned now, right? So all the purpose is we got this condition for stability, and our method is conditionally stable. All right. So now we have looked into the explicit scheme. Now we can look into the implicit one. All right. So how does the implicit scheme look like? Work on this. Why? Only we will change the index. Only we will change the index. So I will write again. So what was our equation, right? This is our equation. This is our equation, right? So what can we do for, we'll now apply the finite difference. Basic next step. What we will get for finite difference? Minus TIN. Imagine the grid now. What will be the denominator? Okay. Yeah. Why delta t? Because you are differentiating with respect to time. So therefore delta t alpha times how it will look? Ti minus 1 minus 2 Ti plus Ti plus 1 by delta x square. Since it is implicit, it will depend on the n plus 1. So here your quantities will be n plus 1. That's the only difference from the explicit method. Can you solve for this? Um, after you rearrange, your equations, you'll come to another equation like this is your matrix equation. How it will look like? Again, we can take R. Again, we can define R. That is like alpha delta t by delta x square, and you can put it R. So, can you how it looks? The final equation. Verify. I will write the equation. Please verify. All are unknowns. You don't do it n plus time step. So these all are unknowns. I n plus 1 step things you don't know. Unknowns. So again, when you consider a matrix for this, you now know how to, this will look like a matrix for different values of I and all. So it will look like a tri-diagonal matrix. Okay. When you put this form of equation into form of AX equal to B, tri-diagonal matrix. You know what is tri-diagonal matrix? Yes. How it will be? Above the main diagonal, another row will be there, another flow of things will be there. Below the main diagonal, another flow will be there. Others are all zero. So I think so in the project, someone has opted for the Thomas algorithm, right? Thomas algorithm is usually like a method to solve these tri-diagonal matrices. How to solve AX equal to B tri-diagonal. So this is a Thomas algorithm. You can solve using Gaussian elimination, whatever you like, but a more efficient scheme than Gaussian elimination will be Thomas here for a special matrix. I would like that group to at least say that the Thomas algorithm is bit efficient than Gauss. Okay. One can ask, why don't you use Gauss? Why you use Thomas? Okay. So this is the implicit scheme, right? So we learned about explicit and implicit scheme, right? Or it is only the change of a notation. Here n plus 1 and n, and you are generating two different. That's it. All right. So slowly we are approaching towards the a very method. Finally, after that we'll have a break. Okay. After that we'll have a break. Let me complete that. Okay. Break of flow. Believe me, it will be break of flow. So you now know. Here I am summarizing everything. Please like pay attention to this. If you came late also, like pay attention to this. It will be clear. How it looks like. T equals to alpha. I'm writing the equation again and again. So you will be in a hang of it. How it looks. So we use Pi n plus 1 minus or dou to T by dou x2 10 steps. Yes. we took the finite difference using the nth time step. Implicit method is the same. It's almost the same as the explicit. But what is the main difference? Yes, all are same. Explicit, implicit. Now, we, depending on these two explicit and implicit methods, we can form a new method that is known as a combined method. The example I can give you a real world application is like drinks. Okay. So suppose like this is your glass. Imagine this is your glass. Okay. And what you are doing, you are mixing liquids. Okay. Maybe one Coca-Cola. Okay. And you mix another liquid. Okay. And you make your drink. You make your drink in such a way that your glass is, am I right? So you're combining two different drinks. Yes. If you want it more strong, you mix the other drink much as compared to the Coke. And if you want the Coke flavor to be more, you mix more Coke. Yes. But in such a way that you don't overflow. It is up to here only, from here to here. Yes. Motivation for this. You're combining different things in such a way according to what you need. So same during the combine, pay close attention to this. It will be the same. Dou t alpha dou 2 t by dou x2. How it will look? The same. The left hand side is the same, but the right hand side will be a bit different. But I should write here. Alpha will be there. So let us not disturb alpha. P times dou 2 t by dou x2 by 10 plus q times dou 2 t by dou x2 at n plus 1. Where? To 1. Can you see? We are mixing. We have to write a second order partial derivative with respect to x. But we are taking a mix of this and a mix of this. P times the mix of this plus q, such a way that p plus q equal to 1. So that makes sense of this string. Now you can understand what I'm trying to convey. Now different choices of P and generate different, solve our heat equation. Okay. And all are valid as long as they are stable and consistent. You can't guarantee that all of them, every numerical scheme will be stable. Then everyone has to check through all the methods we did. Okay. Most common method is Frank-Nicolson or CM, where we take P and Q to be 1 by 2. 50% of that, right? So that is the Frank-Nicolson scheme. Method. I just want to write the formulation for this. How it will look like, can anyone say? So dou t alpha, we have this equation. Can we apply the finite difference to it? Pi n plus 1 minus Pi n by delta t equals to alpha times 1 by 2 over is it okay? So everything is going till now based on our explicit scheme and half of the implicit scheme. Right inside quantity. Now can you find a similar equation as we did here? Like this equation we saw. This equation we solved it, right? So similar sort of equation you will get here also. Try by yourself. Methods. But if you don't solve after you go home within today or tomorrow, then you'll likely forget. So I strongly suggest after going home, make your hands dirty by you looking into the notes. So again, I will write it here. So you should see, I am writing it here because I already have it. You can do the algebra, but I want you to do the algebra at home. Then only you will come to know how it follows. I minus 1 n plus 1 minus 1 pi n plus 1 plus r over 2. You don't need to worry about all this expression coming here. It will be very easy. To the right hand side, left hand side, that's it. Minus plus. Right hand side you will get. Right hand side it is good because you are getting. So what we are doing on the left, n plus 1 quantities on the left, and on the right we are keeping all the known quantities, that is nth step. Anywhere we like. It has a pattern to it. Why we are doing it? You know, this will be acting, the right hand side will be acting like a B. Ax equal to B. It will be acting like a B, and B vector to solve x. So therefore, we have to keep the known quantities on the right. So that's the logic of why I kept all the things on the right. Diagonal system. Again, if you put into matrix form, again tridiagonal matrix, and again more efficient way to use in like Python or coding way is to use Thomas algorithm. So, but Crank-Nicolson scheme is a second order. Shown it is second order, but I'm telling that it is second order, just to know. And it is advantageous over other schemes. Okay, so it is very likely that if Crank-Nicolson, if you are to solve a heat equation, you should actually use Crank-Nicolson. You should not use explicit. So I will ask you a question. Suppose I ask, like, given a heat problem, like which method you should use? Okay, so, and I will ask you a question: can you use explicit method? If not, why? If yes, why? And what shall be your answer? First, explicit method is a conditionally stable method. That means depending on the step size, the stability depends on the step size. So if we decrease step size, spurious oscillation and random errors might grow. Therefore, we will unconditionally stable. Now, do we know a method which is unconditionally stable till now? That's the next one. Till now, we know that explicit scheme is conditionally stable. That means it depends on an equation to be stable. Okay. Calculations, I will write here for the implicit scheme. Steps of the analysis and find the growth factor G by doing epsilon I n plus 1 divided by epsilon I n. I am saying it directly here. What is the value of G? So G will be 1 over this guy. Yes. Now always eyeball this. Think that cos beta always lies in between -1 and 1. Cos beta always lies in between -1 and 1. Eyeball that always, irrespective of what R is, what beta is, always mod G will be less than equal to 1 of your exercises. Okay. Always mod G less than equal to 1. So in order to think, see, this is the equation denominator. Put cos beta values. Put what can be the cos beta values? Minimum -1. 1 can be 0. 1 can be 1. Right? Put the extreme values. Then you can see what is the value here. And then you know, since you have used the extreme values, the values will be like in those values, right? It's understandable. Or no? Shall I repeat? Shall I repeat? Understandable, is it? Yeah. So always eyeball that mod G will be less than equal to 1. What does it mean? If whatever value of R, whatever value of beta, mod G is always less than equal to 1. What does it mean? Step size now. That means in this method, if you use step size as small as possible, still it will be convergent. So therefore it is unconditionally stable. Yeah. Okay. So, yeah, just last part. Just the last part. Yes. So, what are the scheme I did not talk to you about, like finding G? Frank Nicolson. You don't know what is for Frank Nicolson. You can do this method and find that G comes to be like this quantity. This quantity will be given to you. Suppose in exams like this quantity will be given to you. You are not expected to calculate these quantities. G value will be given to you. What is the condition? And some basic philosophical question like what you will choose, what you can't choose, those sort of. So this section is quite important. So again eyeball. Think like why it is a big expression. It is a monstrous equation. Okay, but like 1 and 2 are sine square beta by 2 is there in both numerator. The thing that is differentiating is a minus and a plus sign. Can you see that this guy numerator will be less than the denominator because there is a plus sign? Always. And this guy will always be positive, mod G, like 1 minus 2r sine square beta by 2. Okay. Always here also, always mod G is less than equal to 1. Always. If it was the opposite case, like if you take opposite, like 1 plus 2r sine square beta by 2 divided by 1 minus 2r sine square beta by 2, then it is greater than 1. You can see. Okay, given that I give you these values to you, G values. Okay. Stable as well. Frank Nicolson is also unconditionally stable. Plus, it is a second order accurate scheme. So ask like out of these three methods, which one you should probably use to get more accuracy? What should be your answer? What's the second order accurate? Usually there is no bulletproof like rule for which scheme is better. Depending on your method of use, depending on your method of use, you can select which method is conditionally stable. What happens if you decrease the step size? Random errors might grow. Given the G values, you can find which method is unconditionally stable. Implicit and Frank Nicolson were unconditionally stable. Remember, this part of the lecture will be very important. Calculate. G values might be given to you. Okay, so um, so like pi square will be involved. Check your notebooks. You must have written that formula and it has pi square in it. Check. Yeah. So you are defining x as length space from 0 to 1. So your length of the rod is 0 to 1. And it is getting divided into nx steps. Yes. Same t and u, I am defining it as a like t, I am defining it as zeros of nt. Yes. So it is bit of a bad practice, actually, not a good programming practice. This is like defining u to be like t to be zeros and p dot zeros beforehand. It is not a good practice. But without, I am saying that I want to define my array with some values, some predetermined values, and then throughout my coding process, like looping process, I am going to update them. So that is the basic idea, right? So similarly for T and U, you can see like how it is. It is zeros. It's a matrix of zeros of NT and NX, NT rows and NX columns. Yes. So U exact also, U exact also like you are defining as the same NT comma NX, same zeros element. Now we will update. You will see we will update using the exact solution, and then we'll compute the on top of each other overlap. Then we will see if the exact solution is somewhere and your numerical solution is lying somewhere, then it's obvious that it's not a good method. If they're overlapping on the same, then you know that it's a good numerical method. That means an analytical and numerical solution are pretty close. That you can use numerical methods to solve it. So yeah, these are the initial condition. Use 0, colon. That means you know what it means. Take the 0th row and all the elements of till what you have, the size, is all set to 1. You know this trick, right? Use u colon comma something. That means all the things are taken into granted. So if you want to update the full list along the row, then you can use this trick. Something comma column. If you want to set first row, u 1 comma column. Fifth row, 5 comma column. Okay. Since it's the initial, like the boundary condition, we have to set u 0 comma column. Okay. Similarly, t0 is 0, time step at t equal to 0. Okay. This is the alpha. Can you see? dt by delta x square. This is our alpha, which is 1. Okay. So check your notebooks again. Check your notebooks again for these quantities. Those quantities will be used throughout. Okay. Let's go down. I will tell you this for loop in a while, but let us look the below for loop. First, let us look in the below for loop, then we'll come again to the top. Here, we are defining the exact solution. Here, where for n in range of this, okay, we are defining the exact solution. ut and ux, okay. I told you, since your heat equation is variable separable, t, we can write uxt as some u1t times u2x. These have their own expression. Yes, these have their own expressions. So this is what I have written here. Ut is this equation, ux is this equation. It follows from analysis, pure PDE. Okay. And then what I am doing, np dot outer. What it will do? What will np dot outer do? If array, this another array, and you're trying to multiply them together. What it will do? Np dot outer. This guy will be multiplied. Then a final array will be there. Clear? So this is what I am trying to implement here. I first evaluated this, then I evaluated this guy, then I did an outer to take the multiplication into account. So therefore you can see np dot outer here. Good so far. So in this way we found UEX, which is the exact matrix of the heat equation. Okay, this is the exact matrix of the heat equation. Then you have it. Now what we have to do? Now we have to implement one of the numerical schemes, and we will have U matrix. Now you have U matrix, which is coming from the numerical methods, and you have UEX, which is coming from the PDE analytical method. Then what you have to do? Plot them together. That's the whole idea we are doing in the code. Okay, different time steps so far. Okay. So here also you can see, now move to the top for n in range nt minus 1. So we are using two for loops here. It is varying both in x direction. So we are first covering the x direction here. Cover that x direction, have that set ready, then move to the next time step. Therefore, the x loop is inside and the time step loop is outside. It's not the other way around. You can see why. You can see x loop. So you are updating the x values at each x values. Then you update, then you have a set of like a row full of x values. Then time is on the y direction. Okay. Then what you have to do? You have to make a loop again based on the values now. What is the values at the next time step? Yes. What are the values of the next time step? How it will do? For that, we have an outer for loop. This is for the time, for n in range nt. So therefore, you cannot take the time loop inside and the x loop outside. You can understand why. It's due to the nature of the method we have explained. Nature of the method, like 1 point is depending on the 3 points below. All right. So what kind of method we are applying here? Un plus 1 I, all are depending on n, you can see. So it's a which kind of method? Crank-Nicolson. Explicit. Why? Because to compute n plus 1 step, all are depending on the n step. Everything is written in terms of n. So it's an explicit one. Okay. It can't be implicit. So I don't think it is. Check again. Is it explicit or Crank-Nicolson? I don't think it is crank, because crank is a bit more complicated. Yes. Fine so far. Yeah. So now you have U matrix which stores the your explicit numerical method to solve this heat equation. Now you have UEX which solves the method analytically. All right. Now you have all the data which you need. All the data which you need, both analytical and numerical. What you will do now? Plot to visualize the solution. All right. So here, like, just ignore this. You accept this is just the outer loop, 4 by pi. In your formula, you will have 4 by pi outside. So we are multiplying at the last. So I could have multiplied initially also, but since inside things are getting updated, every time I have to write that 4 by pi. So instead, I wrote at the last. You can write at the top also. Yeah. You can write this here, somewhere here. All right. So I'm plotting U exact at 8,000 step, like t equals to 0.8, you can check, like, because 0.8, why my time is 0.8? Can you say why my time is 0.8 if I'm taking the 8,000 step? It's due to the time step. It's a very tiny time step. So you, in order to reach 0.8, you have to take a lot of iteration to reach there because your time step is very tiny. So here I am plotting the solution for 3 time steps, 0.00, 0.8, randomly 3 time steps. Okay, just to see the effectiveness of my scheme. Okay, so first 3 rows of the code and the plot, they are plotting U exact. That is the exact solution of the PDE. All right, UEX means exact. Okay, then what we will plot? We will plot the U, which are the explicit scheme, which are solved by the explicit scheme. So same here. So same, I should have maintained the consistency, like 8,000, 10, 2,000, I should have maintained in that way, but yeah. So all these things you will see in blue, all right? All the numerical schemes you will see in blue, and all the exact solution you will see in different colors depending on the time. T0.8 you will see in magenta, T0.001 you will see in red color, and T0.2 time you will see the curve in orange color. And all the explicit scheme of different time step, all I have given one color, blue. Okay. So, and you are giving the title of the plot and the X label and Y label. Fine. Legend, I requested a legend. Okay. Say fig or not, it's up to you. Show, yeah. So then, since I have defined this as a main function, I'm calling it. I have defined as definition main. All right. In order to run this, I have to call that function. Yes. So I call that function and you will see some output like this. Okay. So these are the time steps. This orange one is the T0.2. The red is the 0.001. Okay. And T equal to 0.8 is the magenta. All right. Yes. So those are the exact solution. And why are the exact solution? They look like continuous curves. Yes. But when you plot the numerical method, like explicit numerical method, that you will get discrete set of points. So therefore you have these points here. You can see they lie almost like on top of each other. So they are very accurate schemes. All right. So this is a way to say, like, way to visualize the analytical and the numerical scheme. Okay. So what I will do is maybe I can share this code with you. You might keep, might not keep. Okay, inline is like you want your plot to be generated in the same window where your code is. Right? Okay. So if bit of theory for now, not much math for the rest of the lectures. So what is a machine learning? What is machine learning? So machine learning is like a group of algorithms that enhance the learning capability, okay, of not us rather than the computers. How computers can learn, so that they can learn from the data or past experiences. All right. So one example would be like you see, like when you were a baby, so you might have seen like a few cats and dogs, and then you came to identify by seeing some other stray cat and dog that it is a cat and dog. All right. You can differentiate that it is actually a dog and it is not a cat. Yes. So it is all due to your past experiences, what you have learned from your pet at home. Right. So this ability to learn data that is present, that is being presented to us, and later which can be used to generalize or recognize new data, all right, is one of the things we want to the computers to do. All right. So that's where the term comes machine learning, that the machine or the computer is learning. All right. So it's the same, like you can see like some emails which you might get. So sometimes you see like your spam folder has like 3, 4, 5 notifications. Already Google already detected them that it is coming from some spamming sources, and it automatically took them out from the actual true inbox mails. All right. So therefore, your computer, like your mail, Google provider has already learned that how to do, and it is doing it for you. So your email provider automatically separates the good mails from the junk mails, and even the self-driving cars. All right. And many more examples are there. So this is how it is. I hope it. So you have a problem. Okay, you have a problem in mind. Then you check whether it is a labeled data or not. Are you labeling it? Like how you are labeling it? By labeling, I mean you take orange and apple. Okay, orange you label it. Yeah, it is orange. Apple you label it as it is apple. Then it is a labeled data. If you can't label it, then it is not a labeled data. So therefore, we have two cases here: yes and no. If it is yes, learning. If it is no, you go to unsupervised learning. So supervised learning comes into, like, if it is a categorical data, usually category apple and oranges, differentiating apple and orange is like a categorical problem, right? So therefore it comes under this category, like category or quantity, right? If it is a categorical data, you are going to class. Yes, classification. Like whether it is an apple, is it an orange? To classify. Yes. If it is a quantitative data, then you are going towards regression. You're dealing with numbers. You're trying to predict. How is regression from your last semester data analytics? It is like last few classes I covered the regression part. So I gave you a set of data. Then what I did? Then I asked, can you predict what is going to happen at that time? And based on this time step, what should be the value, right? So that is like the regression. So given a set of data, so that is like a supervised learning. You're learning from quantity. So therefore, if it is quantity, you are going to regression side. All right. So here you can see where regression is coming in your ML problems. All right. So learning regression is actually important. Then you go to unsupervised learning. If your data is not labeled, then you have group and dimensionality problems. Grouping, like clustering. In data analytics also we saw some clustering problems, right? Maybe there are many malls and many shops. Sorry, there is a Lulu Mall where there are a lot of tech companies and lot of apartments. Okay, so they have chosen the location in such a way so you can see a lot of huge cluster there, and here in phase 4, not much clusters are there. So you can see the clustering problem there. Okay. So there a lot of clustering algorithm comes, very nice algorithm which I want you to understand or explore is k-means. It's a very nice algorithm. So I'll try to keep your excitement in that. I want you to explore. Many schemes are there, but k-means is very nice. And the dimensionality reduction, we already have seen this in data analytics, like PCA, principal component analysis. We saw like we had an example where we had a huge number of features, lot of features. I gave you an example of like fruit production, I think, apple exports and all, and how what you need, what important features you need, we will keep that. Like size of the apple, how the apple looks like. Is it like if the apple is very like in a very distorted shape, then many users might not prefer it. Okay, thinking that it might have gone bad inside. Yes, so those features are important. So therefore, we take those features at hand, and so we don't have to consider all the features. That way, we are trying to reduce the dimensionality. And one such technique is PCA, principal component analysis. We saw how eigenvalues and eigenvectors are actually yes. How which are the principal components there based on eigenvalues and eigenvectors. Okay, so classification I did not cover, I think, some parts. Like there are many tools which are neural networks, random forest, name, base, and all. Let's support vector machines and all these terms. Courses when you will take. And regression also, like we will see, first we will least square regression in this course. And then I will show you that there is actually a package which can actually do that for you in Python. And then we will see, I think, support vector machine for a tiny bit, like a basic. Okay. All right. So this is all I have already told you about, like all the lectures I was giving, it's all written here. Super. Let's cover that. So basically, you have training the algorithm. So like your method will be trained on. So it will be in this section where it is training, it will be learning basically. Okay. Then you will be testing what it has trained. Then you test on some other mode, whether it actually does that scenario or not. So usually, if you have a data set of 100%, say, then 80% you usually take it for training, and 20% you take it for testing. Okay. No need to worry, like you will learn a lot about this in next semesters, or maybe in this semesters also. Again, we know in supervised learning, depending on the nature of output, if it is categorical, will need classification, and if it is quantitative, you will need regression, right? So again, it's the same example I told you, apple and oranges. So how to know which object is apple and orange? So this is a classification problem. Since the output is a categorical data, that is either orange or apple, so these are known as classes. So this is like a supervised learning problem. Now, if you have like final exam scores based on your homework score, you have some homework now and you are trying to predict what is the final exam score, then this is a regression kind of problem. All right. So this is supervised problem, but it's a regression because you're dealing with quantities now. So another is like unsupervised learning. So yeah, let's not go too deep into this. I already talked before 5 minutes all about this. Okay, dimensionality again, it will reduce the high dimensional problem. So these are some of the main components of the machine learning algorithm. So you are representing your data, then you have some optimization algorithm. You will see why we need to have optimization algorithm. Okay, we'll see. Then you have a tunable model, and then the trained model, which you can actually apply. Like, yeah, you can test whether you can ask the machine, is it this an apple? Is this an orange? Or can you predict the exam score and all? So, and basically we have like encountered this in data analytics previous semester, that we have a lot of different data, like raw data, like you can see documents, images, numbers, sound formats, wave format, MP3 format, MP4 format, text format. So many different types. So how we can deal with this? So we need to turn the data into some format so that the computer can recognize. All right. So now you see how the data analytics part is being connected to this part. Yeah. This same thing we learned in data analytics. Same thing. Lot of data of different types in terms of data integration. All right. Data integration. Right. So here we have a feature matrix. Right. So you have now what are the features? Apple, and what are the features of apple? Shape, size, weight, and color. Yeah. So these are the features which is you can see on the set. Okay. And the number of samples which is in the column set. Okay. So you take the different samples of oranges, different samples of apples and oranges, and you do the same for them. And from that you develop a target. Okay. You can see the rows are like apple, orange. Columns will be like size, weight, shape, and maybe taste. Maybe some apples are very sweet, some apples are like sour and all. Okay. Yeah. Again, a bit of a lot of things. Yes. So we have 3 things here: the tunable model, the optimization algorithm, and the trained model. All right. So tunable model is like if you have the input and output data ready. See, you have in these sort of models, you have output data with you. You know that it is an okay, and you are feeding this to a model so that it can learn from it. Okay. So therefore, we need an algorithm that can learn from the data. Is not the problem here for a tunable model. Rather, an algorithm is the problem. How you can write an algorithm such that it detects whether it is an apple or orange. Okay. Sure, your algorithms will have a lot of different parameters. Okay. So which parameter you have to take is up to you and depending on the problem. Okay. So you will see in many machine learning algorithms, you will have F score and a lot of different parameters will be there. So we might see in a code. So, and you need to change it according to your need. So many tunable models such as like ANN, artificial random forest, logistic regression, and so on. Okay. Optimization algorithm. Now we saw like how regression is coming into picture. We can also see why optimization is needed. So as you can see, this is the main working force behind these machine learning algorithms. So we need to tune a model, all right? But how we can do that? How you can actually do? Usually we define an objective function. Sometimes we define an objective function and we use optimization algorithms to actually optimize it, like minimize it or maximize it and say that, yes, we need this kind of tunable model. Okay. So sometimes you need to optimize things, optimize your tunable model. Okay. That's where you need optimization. That's where optimization comes to picture. Okay. So I'm trying to motivate you why you need to learn regression and optimization. So therefore we need to do all this. Anyway, so you can see like there are different optimization algorithms. Like there are many different optimization algorithms. Fam. So like gradient descent, least square, and all these things. Okay, least square we'll cover here. Gradient descent I will try to cover here. That's the important part. Gradient descent I think you are learning somewhere else also. Predictive analytics. Okay, so shall we cover it here or not? How many years? 1, 2, 3, 4. No? The question is like you are already learning gradient descent in predictive analytics. So shall I cover gradient descent in this course? If you say yes, raise it. Oh, such a strong support. Good. We will cover it. Okay. So trained model, like after you tune the model, it has now, after you tune the model, now your model is ready. That means it is in a state of classifying. It is in a state to classify things. It is in a state to do regression also, to predict. All right. So yeah, this trained model can now be used to for the new data for achieving your goal. All right. Depending on the problem you have. Again, we'll just cover the classification a bit. All right. So yes, we want to classify some products into bad quality. Like you can see, like emails into good or junk mails, books into interesting or boring. All right. So two key factors makes a classification. First thing, it should be labeled. It should be a labeled data. Then second one, the output we want should be a categorical data. That is yes, no, or something like apple, orange, or anything. So you can see that this is a binary classification. You have apple and orange here. And why I'm saying that it is classification because you have only two things, apple and orange. If you have three things, then might be different. So now you can see this is the feature matrix. You have color, texture, shape, smell, and has a core. Usually apple has a core, right? Seeds. Orange doesn't have a core. So that's also a feature. So, and these are the targets. We'll see what is the target, but again, the target will be like a 0, 1 here because it's a binary classification. If not a binary classification, it will be a set of numbers. Okay. So here we have five features, but how you will visualize 5 features? The same problem we faced during data analytics. Okay. So we can start by visualizing 2 features. That is like dimensionality, reduction. Okay, we reduced our dimension to 2 and take the two most important features which you will get by PCA. Okay, and those two features will be your output. Those features you can take and visualize your data. Then comes your data visualization, which we talked in data analytics. All right, now you can see a link between all this. Okay, my aim was to show you the link between all this. All right, so classification means like I want you to please like hold on to this because things are going a bit interesting now. Please hold on. All right. Okay, so classification means what? It is intuitive and trivial to say this part is orange, this part is apple. But mathematically, when you say this, that means you need a boundary between them. That is in machine learning jargon, it is known as a decision boundary. Okay, so this curve you see, like I have plotted color on the x-axis and texture on the y-axis. Orange. All right. Apples are red. Oranges are of orange color. Okay. Yeah. And then you can see like the y-axis is texture, like it is rough. Okay, and then going towards the smooth. All right, these are the textures. So, and here you can see, I think the blue ones are the apples, and I could have made it red. And then later. Then the orange ones are the squares. Okay. So you can see machine learning has classified it. What does it mean? What does it mean? What does it mean? If it is classifying, it means that it will separate them together. Okay? It will separate them together. That means you will have a decision boundary. Okay? That's it. That's the main concept in mathematical terms. So see, that's what all have boundary, either a straight line or it can be a curve also. We will see a code here soon in Python where you can see that the normally it's a straight line, but you can have a curve also. So the tuning of the algorithm is basically to move this line and find out the shape of the boundary. Okay. So how your Python code can do this thing? There is a module in Python from scikit-learn. Okay. Support vector machine. So I would ask, we'll start. I would ask like which line is better? Is it the red or is it the black dotted? Hmm? Yes. How many red lines? How many red lines? How many black lines? How many black lines? Raise. Why are you fearing? Raise. Sorry, the red one wins. Why is the case? Okay, so if you see the black lines is not a good candidate. Why? Suppose now I have a new data to add. Suppose I want to add a new apple. Okay, this line is very close to apple boundary. It might be that I will put that apple and it will cross the boundary. Okay, but you are in a very good chance if you take the red line because you have a lot of space. That is, you have a lot of distance, much distance between the corresponding classes. Which red or black? Black is more closer. So you are more prone to errors. Okay, so red you can keep. I can keep an apple here and still I am fine. Okay, but if you choose the black one, it's not fine. All right. So this is what is like support vector machine SVM, a very intuitive algorithm based on how we make a decision. All right. Okay. So we'll see. Yeah. What happens if you add a blue circle next? If it is not predicting correctly, right? See that you can understand it, right? So therefore the model which has the line close to the middle of the gap and far away from both the classes are the better ones. Red ones are the better. This red decision. So this is just the intuition we have. Now, how you can put the is creating the tunable mode or algorithm. Okay. So this is the design of the SVM algorithm. It first forms a buffer from the boundary. We will see what is a buffer. Okay. Just it's the logic, just the intuition what we learn. So it forms a buffer from the boundary line to the points in both classes that are close to the line, and these are known as the support vectors. You will see from the decision boundary, we will point a vector to each of the data points. Okay. And these are like support vectors, and therefore you have the name of support vector machine. You always wonder, everyone is saying support vector machine, but what is actually, where actually it came from? It came from the support vectors. Okay. Right. So then the problem becomes like, yeah, given this set of support vectors, which line has the maximum buffer? So you can see like this is an optimization problem. Okay, we are saying like, yeah, given a set of support vectors, then which buffer is the maximum value? Now you can appreciate that this is indeed turning to an optimization problem. So we have to learn about optimization. Okay. So you can see what I mean by buffer. What I mean by a buffer is like you can left this has a wide buffer. This is a wide buffer, okay, and because you have a lot of spacing between the two classes, all right. But if you see the right hand side, it has a narrow buffer. Okay, why? Because it's very close to the data points or the classes. So a wide buffer is generally good. Our problem is that, right, we want to maximize the buffer. That's what I told you just before, right? I want to maximize the buffer. So the black dotted line, we have, this is what I have told you. So yes, the most popular packages for general machine learning is like scikit-learn. So always we will be importing scikit-learn wherever we are doing some ML algorithms. We'll always import scikit-learn unless you are in your computer system. So it contains many different algorithms which you will see, and yeah, there are also many more packages towards deep learning, like TensorFlow and PyTorch, which you will be learning in your third sem, I think, third semester deep learning. So there you can see this TensorFlow and PyTorch. Okay, so we'll move towards the lab session a bit. Okay. But okay. Classification in Python. So as you can see, we will import NumPy as always. Import iter tools. What is iter tools? We'll see. Import Matplotlib, fine. From sklearn, import SVM and datasets. Okay. So sklearn, yeah. So I have written it here. Is a module. What is it? What it will do? So it is a versatile Python library that provides function for creating or looping constructs. Okay. So mostly like if you want to do some sort of like a permutation and combination and all those things, then you have to import iter tools. All right. So, and also like from sklearn, as I already told you, we will take that SVM module from that. Dataset modules also is there. Why we are taking it? See, if we are doing a novel problem, like a new problem, we don't need to import datasets. But we are planning to take a dataset which is already pre-existing in sklearn. That is an iris dataset, like flower, different classification we do depending on the petals, flowers, and all. Okay, so dataset and yeah, classification report. This is a function we are importing from sk.matrix. What it will do? It will allow you to generate the text report showing the main classification matrix. Okay. So just you don't need to worry about all this. Just I wanted to give you an introduction. Has it been covered by any of the courses till now? So this is just a basic overview of machine learning, just to motivate you. Okay. So we will take an iris data set, like classic data set in the field of machine learning, and there it has like 150 samples of iris flowers. I urge you to Google like about iris flowers, how they look. There are around 4 different types of flowers. Okay, different types of, and machine learning, we will use the machine learning to classify those 4 different types, and we will find a decision boundary between those data sets. Okay, so you can see sepal length, sepal width, petal width, target variable, all this. I think BioAI, if they could have here, they could have been. Anyway, the iris variable will have like a dictionary like object, but it will have data. That means a feature matrix. We just show like what it will have. It will have numeric features. Okay. Target variable, numeric labels consisting of different species. Okay. Target names. What are the actual? We'll see different types of name of iris flowers. Okay. Feature names, feature or attributes in the data set. And this is like a description of the data set, DESCR, like a short form. So here we are basically doing that. So we are loading the iris data set, like datasets dot load iris, okay, and that is stored in iris variable. Now you can extract every information from that iris. How iris dot something, will give you different things. So iris dot feature names, what it will give? Iris dot feature names, as you can see the output below. Feature names are like sepal length, sepal width, petal width. Good. Iris dot target names. Target names are like, these are the 3 different kinds of iris flowers, like setosa, versicolor, and virginia. Okay. And how many number of samples this data set has? Predefined 150. And how many features it has? 4. Why? You already saw that in the first case, feature names. 1, 2, 3, 4. But we are doing, let's print only 10 samples. So it is printing those 10 samples for you. So you can see each of the rows, I think, has 4 values. Those are for 4 different features. You can appreciate it better, okay? So these are the 4 different features you see. And these are the same, like print the target names, like the feature, what are the different, these actually we will classify, okay? So there are many features as we saw, but we will be using 2 features, all right? So what features will we use? We will use target name and feature name, all right? So yeah. Anyway, so it's quite interesting as well. So you'll see that, yeah, I have assigned colors and symbols for each of them, and then I'm doing a scatter plot for them to plot the data, how the data set looks, how the pre-existing data set actually looks. That's the idea. We will cover them in next class again, no worries. But I want to show that this is how the data set looks. You can see 1, 2, 3. 3 different patterns, 3 different types of flowers, 3 different colors. Okay. You can know our job next is to find the decision bound for them. So you can see like there will be one decision boundary below, another decision boundary above. Okay. That's our job next time. We'll see what are the steps. And we'll actually find the decision boundary. Okay. Yeah, this we'll see in the next class. Okay. So next class we'll start with this, and we'll go to least square regression. Okay. And then we'll come to regression from a machine learning point of view. Then last part of the course will be optimization. So yes, wait.